Good afternoon, everybody. My name's Steve Knight. I'm the Program Director for the Digital Preservation Research and Consultancy here at National Library. Basically, our job is to start to think about what it means to carry digitally created material through 50, 100, 200 years. The library has cuneiform resources going back 4,000 years. We've got over 20,000 objects of rare books that are from 1469 onwards, and we're fairly comfortable with what we know, what we're supposed to be doing with that stuff. We also have now 1.6 million what we call intellectual objects in our permanent repository for digital collections. And an intellectual entity could be a single image, it could be a 300-page manuscript, or it could be a 2,000-page website. So all up, we've got over 500 million files, 1.56 million intellectual entities, as I mentioned, and about 172 different formats of digital stuff in our collections. What we can't say today is that we know what we're doing with that stuff in the same way as we can with the historical material that we've traditionally collected. Which brings us to this week. The library is a member of a thing called the National and State Libraries of Australasia, so that's the 2 national libraries and the 8 state and territory libraries of Australia and New Zealand. And the NASLA grouping has a thing called a Digital Preservation Working Group. And it's the Digital Preservation Working Group that has put together this series of events this week for what we're calling Digital Preservation Week. So that's all from me. I want to hand you over now to Peter Griffin. Peter is the founding manager of the Science Media Centre and also the founder and editor of SciBlogs, and he'll be the facilitator for today's session. So if you would join me in welcoming Peter.
Look, as Steve said, my name's Peter Griffin. I run this little unit called the Science Media Centre, which is at the Academy of Sciences just a road over. It's called the Royal Society of New Zealand. So we're working every day with journalists like Veronika, people who are covering science-related issues. I'm also a columnist for the New Zealand Listener. I was a tech reporter for a long time before I joined the Science Media Centre. So this event, this week, really looks like it's been engineered with me in mind. Science, the digital world, which is what I cover in the Listener. My favourite movie tonight, 2001. So I'm in heaven. Forget the film festival, this is it for me. So look, we've got about an hour, and what's going to happen over this hour is, first of all, we're going to play a vodcast, which is Dr. Alan Duffy, who really wanted to be here, but unfortunately it's just snowed under, so couldn't make it across. That's only going to be about 10 minutes. Then we're going to hear a presentation from Veronika. There'll be some slides. And then we're going to have a bit of discussion, and really that's an opportunity for you to throw in your questions from the floor. Any burning questions you have about things like dark matter, about the square kilometre array, anything you want. But really what this is about is the preservation of all of that big data that is coming out of all these big science projects that are happening around the world, and some of which New Zealand scientists and researchers are involved in. So it's posing huge opportunity for research, but huge logistical challenges for how we preserve that, curate it, make sure that it's in a good format for researchers now, but also in hundreds of years' time as well. So I'll kick off just with a couple of brief bios for our speakers today, and then we'll get straight into Alan's vodcast. So Dr. Alan Duffy is an astronomer and research fellow at the Centre for Astrophysics and Supercomputing at Swinburne University of Technology in Melbourne. He's co-investigator of the world's first dark matter detector in the Southern Hemisphere. It's called SABRE. They're drilling it out as we speak. And he's a member of 2 leading surveys on the next generation Australia Square Kilometre Array Pathfinder telescope, which Veronika recently visited, so we'll be talking about that as well. Now, Veronika is a science writer and broadcaster, author of several books on science, including Science on Ice, Discovering the Secrets of Antarctica and Atoms, Dinosaurs and DNA, 68 Great New Zealand Scientists. Until recently, you'll have heard her as co-host and co-producer of Our Changing World, the science show on RNZ that ran for 16 years.
In different
different incarnations. Most of those years,
Last 10 of that
yeah, was Our Changing World. So Veronika's been there throughout. That show has been scaled back slightly recently with some restructuring. Veronika's no longer at RNZ, but still committed to science journalism, has all sorts of outlets now, including in the digital realm. So if you're tweeting today, we're more than happy for you to tweet anything you hear or see here. You can follow Veronika at Veronika Meduna with a K, Veronika with a K, at Veronika Meduna. Alan as well, it would be great for him to hear some shout outs from across the Tasman. He's at Astro Duff, that's his handle. And also the National Library is on Twitter, if you didn't know, at NLNZ. So feel free to tweet, and hopefully we might even see some questions. I'll keep an eye on the Twitter feed as well. Okay, so we'll hand over now to Alan via vodcast.
My name is Dr. Alan Duffy. I'm a research fellow and astronomer at Swinburne University, and I create baby universes on supercomputers. I do this to try and figure out how galaxies like our Milky Way grow and even formed. Right now it's a bit of a mystery as to why the galaxies are there, why there's so many of them, why are they so big. One of the key ingredients appears to be a mysterious new type of mass that we call dark matter. We don't know what it is, but if we don't put it into our simulations, we just actually can't form a galaxy at all. Now, I'm aware that the dark matter is out there, but I would really love to know actually what it is. So to that end, I'm helping with the world's first dark matter detector in the Southern Hemisphere. It's called SABRE, and it will be based in the bottom of a gold mine in Stawell in Victoria. And we're desperately trying to find what this dark matter actually is. And when we do, we'll have suddenly discovered more about our universe than we had ever previously known. So technology in my role is absolutely key. I create these universes on powerful supercomputers. This is a room filled, humming with computers just like you might have at home, but maybe 10 or 100,000 of those. And on those supercomputers, you can watch galaxies grow. Now, behind me is one of my favorite baby universes. It's a few 100 million light years across. Each of those points of light are actually entire galaxies, and strung between them, we see the dark matter filaments. All of this would not be possible without the latest in computational hardware. Astronomy is a social science. We are always communicating with each other. We're always swapping ideas, sometimes not so politely, sometimes very constructively. And that communication is made possible through the internet, but also sharing of the data. These data sets that stream down from the telescopes are terabytes in size. It's actually blowing our minds how we're going to get the data from the latest telescopes, including the Australian Square Kilometre Pathfinder. It's nearly finished construction, aiming in 2016. And at that point, there's going to be so much data pouring off this, we don't even know how to transfer it. It is going to be a beautiful problem to have, though, because with those latest images, we'll be able to explore the very furthest reaches of the universe and hopefully figure out how you get a galaxy like our Milky Way. Most astronomers today will never actually go to the telescope that they're using for their science. Thanks to the internet, thanks to digital platforms, there's just no reason to go there and take those images yourself. You get it delivered to you. Even more than that, thanks to the amazing digital platforms that provide citizen scientists with these images, we can crowdsource tens of thousands, hundreds of thousands of people to help us analyze our data. If you don't save that, you'll never be able to go back and explore it again in a new way or ask different questions that people can explore those data sets for you. That means preserving it is fundamental, and it's fundamental to the process of science, which is all about repetition. If you can't repeat your experiment, it's not science. It was just a fluke. So what do you do when you delete that information, when you delete that data? 10 years from now, someone wants to recreate the observations that you made or the analysis that you performed, and the data's gone. It's not enough just to claim it now and write it up in a paper. You have to provide the data as well. and that means digital preservation is the key to science in the future. We try to store, we try to preserve as much information as we can in the hopes that the next generation will be able to ask better questions and explore that data in a better way than we can today. One of the key principles in science is that your data is shareable and understandable. And scientists are a little bit lazy. We're trying to focus on the discovery, and we're desperately trying to make that right now. And we don't often think about how easy is this going to be for the next generation of scientists a decade from now or even longer. How easy is it going to be for them to read my data, to understand what this vast data set actually is? If we don't preempt and design the preservation of our data in a way that is flexible and easy to understand, then we risk entering essentially a digital dark age where there will just be this period of decades where all of the amazing discoveries and the data that made that possible just can't be read. That the storage medium has changed. We used to have floppy disks. I haven't seen a floppy disk reader in like a decade. If someone were to give me that and tell me there was a Nobel Prize winning bit of research or data on that floppy disk, what could I do? It would drive me nuts. But this is where we're at right now, and if we don't future-proof our data and build in preservation from the start, then very likely the next generation will be cursing us for not having made that extra bit of effort to make our data readable and preservable. Big institutions have a responsibility to store and make accessible the data as much as the discoveries themselves. And we're at a time where you don't just have to take my word for it as a scientist. You can explore the data and you can see how many galaxies are in the universe, and you can make these measurements and check that we did it right. I'm not saying it's easy, but I'm definitely saying it's possible. And as the tools get better, and thanks to the internet and all of the digital platforms that are being created, it's actually feasible that you go into a library, and whereas before you might read a book about galaxy formation, now you could actually use my simulations and watch a galaxy grow in front of you, actually explore its properties and see how they change in time and different physics. That's all currently possible. Now, if it's practical or not, that's another issue, because a book does not take as much storage as one of these simulations. This object behind me has 1 billion particles in it. The entire catalog is well into the terabytes. Right now, that's an extraordinary ask, but technology progresses so quickly that maybe for the next generation, this would be a trivial amount of data to analyze, and it would be as simple as checking out a book at a library, is to sit and explore it and find out for yourself exactly how galaxies form.
I was going to have a backdrop of Alan's baby universes, but instead, do you remember when he said that astronomers really get to see the kit that they work with, the telescope? So I've just done that last month. This is in the middle of nowhere in Western Australia. So to get to this spot, Alan referred to the square kilometre array, and this is one of the Pathfinder telescopes. So imagine you get to this, you get to Perth and you fly for an hour into the middle of nowhere, you land on a dirt strip at a homestead, then you drive for another hour, and then you get to this place in an area that's about, think the bottom half of the South Island, that sort of area. There's 100 people living in there. I know the South Island is sparsely populated, but that is seriously sparsely populated. As we were driving in there was kangaroos, obviously, but wedge-tailed eagles sitting on the trees around us, some giant monitors of some sort, lizards walking across the road, so the bus that was carrying us would have to stop, and nothing much else. These dishes that you see there, this is the square kilometre array Pathfinder telescope that Alan referred to. A little bit of history about this particular project, because New Zealand is a member country in this one as well. Initially, New Zealand was hopeful that we would have some of the kit here as well, but that didn't go through. In the end, the decision was made that Australia should have some of them, and the other half of this project is now in South Africa. So they'll have dishes in different types of antennae. I'll just show you another picture of it, just for the beauty of it, really, this one. But New Zealand is still involved, and I'll talk a little bit later about the data flows from this. This is where New Zealand comes into it. But first, let me describe to you the site itself. It's what's called a radio quiet zone. So there's no internet, there's no Wi-Fi, mobile phones, nothing really, no radios, no television, nothing. There's a handful of people working on site. The only way they can work there, because they use computers obviously, the only way they can work is they're in a building that is wrapped in a sheet of metal like a Faraday cage, and they go through double doors in and out. And that's to keep it radio quiet, because really these telescopes are tuning into the faintest of radio hums in the radio wave spectrum. So you want to avoid any kind of interference with radio waves that we produce constantly. The innovation in these dishes, and I have one more of that, the innovation there is that if you think back to the movie The Dish, that's our idea of one of these dishes. You kind of point them at a point in the sky, you take an image, and then to see something else you have to point it elsewhere constantly. The innovation there is that they've come up with the equivalent of a wide-angle lens on a digital camera. So these dishes now, you still can move them, but every time they take an image, it's not a point source, it's a wide-angle picture of the sky. And like in the transition from, say, an analog to a digital camera, of course, the amount of stuff you produce is much larger. So already we're talking about massive amounts of data, an increase in data flows. On the same side, with these dishes, there's 36 of these, or all of them 12 meter in diameter, so huge. You can probably see a bit of a scale comparison with the people there. The other side, on the same square kilometre array side in Western Australia, is called completely different also telescope, but different setup really. That's called the Murchison Widefield array, and they use these dipole antennas. Hundreds of thousands of them already, and will be built up to around 1 million, so there'll be a lot more of those. They are tuned into a different frequency. So the dishes take one frequency spectrum, and both in radio waves. These ones are tuning into very low frequencies in the radio spectrum. So they are really, the focus is what Alan was saying, galaxy formation, and also looking for pulsars, but they're really looking for hydrogen. In many ways, the history of the universe is the history of hydrogen, or the other way around. The history of hydrogen is the history of our universe. It's the most abundant chemical element, and it plays a significant role in early star formation. These antennae can look at the point where the first hydrogen was burned, and it's in my terms, I would refer to it as the cosmic dawn, really, the first light of the cosmos. And the reason why we can look for hydrogen now is that hydrogen emits at 21 centimetre or thereabouts, I think, so centimetre range. But by the time, from that moment of first hydrogen being burned, by the time these centimetre length waves travel through time and through the universe, they're several metres big, and this is exactly what these antenna can receive, or they're tuned into receiving. There's a lovely image that one of the astronomers that I talked to described this sort of pointing or scanning the dawn of the cosmos to me, that if we know that the universe is 13.8 billion years old, so she said, well, just think of it as a nearly 14-year-old teenager, then what these things are looking at is the first 4 to 6 months in the life of this teenager. So that's how far back they can look, really, to this beginning. Now, Alan mentioned this site. These antennae and the dishes are already there, and the future, beginning in 2018, the construction will then include these kinds of antennae. So this is the actual square kilometre array. This is what's going to be shared between Australia and South Africa. Alan also mentioned the Sabre facility, this old gold mine that they're using to detect dark matter. And of course, both of these are producing incredible amounts of data, because they're gathering everything. Those antennae are gathering everything that comes from the universe. And this is another point that I want to refer to that Alan mentioned, is this idea of the digital dark ages, that there's a chance that we, by simply not storing all these things that we gather without necessarily knowing what we're getting there, we might be missing something that will be of importance later on. We probably are missing something that will be important later on. And in my trip, I visited the supercomputer data center. And that the term that I'd never heard before and I learned there was petaflops. That's the speed at which they are processing data. And I'd have to read this out to you because I would never remember. But a petaflop is a measure of not just the size of data flows, but the actual processing speed. And it can be expressed as a quadrillion or 1,000 trillion of floating point operations per second. Floating point operation is flop. And the petaflop is essentially 1,000 teraflops. So we're not just talking about huge amounts of data, but also the speed at which it's going through these computing centres. New Zealand is a member country of the Square Kilometre Array, and that's exactly where New Zealand comes in developing the data processing methods and mechanisms, and also in developing algorithms to look at the sea of data and fish out the things that are of interest now. And now is the important point here, because that's where when you start thinking about preserving these data flows, what we know now, what we might be interested in, and what we're developing algorithms for is literally only in the present. 10 years down the track, everything from the coding languages that we use, from the data processing mechanisms that we use, will have changed. And the questions that we might be able to ask of the sea of data will also have changed. So how can we even think about preserving enough to be able to question it differently further down the track? And I've sort of made myself a note here about sort of remembering the two different kinds of limitations. It's on one hand the technology that we have today to use, but also the imagination that we have today to ask questions. Both things will change significantly. Chances are that technology will also speed up. So it's not only going to keep changing, but the rate of change will also be increasingly faster. So what are the kind of questions that future astronomers will be asking from these data? And where is the raw data entry point? At which point do we need to start storing everything? Or is there some way of preserving things that we could predict will be of interest? Now, this is just astronomy. Think of genomics, think of the vast amount of environmental data that we're now gathering just to have it. For me, I kind of watched Alan and I thought, well, I can see a parallel between genomics and astronomy. And for me, genomics is possibly even slightly easier to contemplate in a way, because think of the genomes that we're now coding or decoding, deciphering. It's not that long ago that we did the first human genome. Now we're sequencing genomes of every living kakapo, for example. Lots of different species. And we already know that it's a very small percentage of the sequence in the DNA that we read that is actually a gene. So the stretch of DNA that literally can be translating into another code that then makes a protein. So the genes that code for proteins. The majority of it is what used to be called junk DNA. Now we know it's not junk. We know it's probably there for something. Some of it may be true junk in the sense that it's just repeated sequences that just happen to be accumulating while DNA is mixing everywhere. But a lot of it will probably have some meaning, but we have no idea what, or very little idea of what it is. The same in astronomy. It's a tiniest percentage of the universe that we can see with the methods we have now available to visualize. More than 90% of it is this dark matter, stuff we know is there but don't know quite what it is. Alan has a lovely way of describing dark matter. He kind of thinks back a few centuries when scientists knew that there's air, even though we can't see it really, but they knew that, and they understood the concept of air because we notice it as wind. It rustles the leaves in a tree, so we know it's there. In the same way, there's movement in the stars that cannot be explained in any other way other than this dark matter. So while we have no way of knowing, like a few hundred years ago, people had no way of knowing that in air there's oxygen and there's other elements that we cannot see or cannot touch or anything. But as a force, it is there. There's something there that creates a movement in stars that cannot be explained in any other way. So before we get into the discussion part of this, I'm just going to run you through a few thoughts that I've picked up from Alan's talk. Firstly, data storage in this digital age is, let me just check, is significant simply for scientific reasons. Science builds on itself. So for future science questions, we need to still have access to older science questions. There's also the issue of reproducibility. If somebody discovers something, it has to be reproduced by another team, and ideally it keeps being reproduced on this pathway of science building on itself. So for purely scientific processes, we need to have the raw data in some form. There's also the idea of data sharing. So between different teams, data needs to flow as freely as possible. Should it be open source completely? Should that be something that needs to be discussed as part of this preservation discussion? Alan mentioned crowdsourcing. The more data we produce, the more likely it is that people will be called upon to help with analysing. And astronomy is a perfect example. It's always been a citizen science in many ways. There's always been people who have contributed observations, starting from purely visual observations with people with their telescopes in their own backyards contributing. Now, obviously, it's more that you get a data set and you try and analyse it. So that will apply to other areas of science as well. Future-proofing. This is the idea of allowing for future questions that are unimaginable now to develop in the future. The change in all aspects, changes in the coding language, changes in the technology we use to process data, changes in the algorithms that we develop, changes in the protocols that we use now to work on the data. All of this will change. So how can we future-proof all of these processes and allow for development in the future? I love this image that Alan left us with of, imagine in the future you go to a library and you don't issue a book, but you issue a simulation that you can possibly even take home on some sort of portable data system that you plug in and watch. But whose responsibility is it to do that? Is it the scientists that need to think about it? Is it the national libraries? Where lies the responsibility for this? And lastly, I'd like you to kind of think with us about the idea of curation. Do we need some way of putting the data away into safe storage with curation in mind? And at that point, we can kick this off. Do you want to come back here?
Sure.
I'll get the,
Here we go.
You take this and I'll take
You jump out front there. And, wow, well, so much covered there, so many questions. I hope you've got questions, because we're going to throw it open very soon on data preservation, everything. But I just wanted to start with the science, really, just a couple of questions about the science and dark matter in particular. we won't go too deep. Coming over here so you get in screen. Before Einstein came along, there was this idea of this ether, the luminiferous ether, I think it was called. You know, scientists at the time thought that matter, everything was embodied by something, and this sort of field, they didn't know what it was. It seems like where we're at now with dark matter, which was first theorized in the 1930s, we're sort of at the point now with the Sabre installation, and this is a kilometre deep, so that there's no other radiation that can touch it. They've got a very sensitive crystal, or will have, at the bottom of that mine shaft that will detect dark matter, or literally will glow when it detects dark matter. It's mind-blowing sort of stuff. How significant is this, do you think? I mean, there's no Nobel so far for dark matter. It could shatter the standard model of physics if it is discovered. Is this one of the biggest scientific challenges still out there?
I'd imagine it would be on the scale of the Large Hadron Collider discoveries.
Yeah.
Similar in many ways, a huge scientific facility that finally discovers the one thing that was theorized. We knew it should be there to make sense of the the way we imagine that physics works or the universe works, and then they discover it. And this would be even bigger because it is really the biggest part of the universe that we know nothing
This
about.
is 85%, they think, of the mass of the universe is actually dark matter.
Yeah, and dark energy, and however those, you come to 90-odd% with dark matter and dark energy, and however those two are distinguished, I wouldn't be surprised if there's some connection that once we discover one, dark matter, it will also make clear what we think dark energy is. So yes, it would be. I can't even imagine how big that would be, because it would really not necessarily throw out, but it would make us rethink what we've explained about space so far.
Wow. And then, of course, square kilometre array as well. Now, and this is interesting because it's actually spread over 2 continents. So you went and saw some of the sites in Australia. There are all these other sites that have been constructed in South Africa. Why is that? And it also poses some interesting challenges in terms of real-time data collection from arrays on 2 different continents.
The decision, finally, there was geopolitics involved in that as well. The original proposal with New Zealand involved was about having a bigger geographical spread, just so that one dish would have been here and that would have given more area that covered. Now that, of course, is bigger still, but in the final decision there was geopolitics in there as well, that it would be good to have a large project like this. And it is an international project with a number of countries involved in putting money and resources and ideas into it. It would be good to have that in a country that can do with development in that. And it has created jobs in the sites, but also just the scientific community was really invigorated by that.
Right. And then so you've got arrays like those weird little spiders that you saw, and also radio telescopes in the African subcontinent collecting all of this data. It needs to be matched up with data coming off the arrays in Australia, so they get a full picture, they get the full expanse of this array.
There are different frequencies. So the Australian side is in the low frequencies, like this hydrogen target. The South African side will be in a higher frequency range. So they won't actually necessarily need to be compiled in one pipeline, so to speak. The initial data processing will happen on site, and then they'll have their own supercomputing center where it's almost like you literally get an image, and I think Alan was referring to it as an image. So the data flows in, and then in those supercomputing centers they will be turned into an image that the astronomers then analyze. And it's at that point where the exchange between the different countries involved will happen. So not so much, because you wouldn't want to transport the data across the world. That would drown you in a sea of data. It's until after this point of imaging it to something useful under today's questions that it will be distributed among the community of researchers.
Right. And what's the sense you got from the scientists involved with the SKA? Do you feel that they have a robust plan in place for storing all of this and distributing it around the world to researchers to work on?
It goes in stages, and each stage has its own budget. So I think, yes, robust, but I think they think in those time stages. And the ASCAP, the Pathfinder, those big dishes, were in fact developed to, if everything else falls over, to be their standalone telescope. So the science questions that they developed are for each of those stages separately, so that if, say, global finance has other priorities, then it may not continue after a certain point. But as far as the data flow is concerned, one of the people here in New Zealand spoke of that as a parallel development. So the ideas of how to process the data is only a few steps ahead really of the increase in data flow, which is good because it really pushes that development. You couldn't think of a better motivation to keep developing it, but it is robust in the sense that they are ahead of it, but it's in a parallel process. And the same for those algorithms. That's one way of managing the data flows in the first place, but then also to start pick out the things that you want to look at in detail. That's almost like they're all running in parallel.
And they're literally using parallel processing, aren't they? A new form of processing where you can split up jobs and different processors work on different part of the job, so you can more quickly get through a very complex equation like will be produced by this telescope.
Yeah. In terms of data storage though, and you might even know more about how that would be possible in the end, but the way I understand it is that all raw data is processed and imaged, but not stored. The storage begins at that image, at that first analysis. That's my current understanding.
Right,
And this is,
yeah.
I think that's one of the issues here, that will we in the future really need to go back to the raw data. The raw data in this particular instance really means everything that comes in that frequency out of the universe. So there's a good chance that most of it is of no interest.
Yeah.
But do we know?
Yeah.
Do we know whether it will be of interest at some point?
It's sort of similar parallels to another big science project that both of us were lucky enough to see recently. It's the Sofia Telescope. It's an infrared telescope built into the side of a 747. If you've been through Christchurch Airport, you'll have seen the NASA tail there on the plane. So that is a 17-ton telescope that is actually taking infrared images of the universe. And I was on the plane recently, Veronika was separately, and what you actually see there is just someone's laptop screen with all this data coming off the infrared telescope. So again, you've got a huge amount of data, and researchers around the world bid for time to spend on this telescope. It's very competitive. Only a small number of the proposals are accepted. And what they then get sent is all of this data to wade through and look for their particular question that they're searching for an answer to. So again, you've got, and the synchrotron was another one you went to recently, you've got all of these big data projects, and it seems as though the data
if you widen that to genomics and to biology and to environmental science, there's so many projects that would use far more data than we can possibly ever analyze now.
Yeah.
So what do you
and
do
they seem to be kept separately. There's all these silos of big data everywhere, which maybe the scientists are responsible for keeping. There doesn't appear to be any sort of curation overall of all of this. Do you see that posing big problems long term?
It depends which way we move with open data. When you think of the Human Genome Project, that started out with one privately funded enterprise and one public enterprise. That alone seems to be heading more into open, publicly funded and more open source. If we're heading that way, then I think that it would also be a kind of a public discussion to be had how to preserve the data. If it's increasingly privately funded, well, then you end up with IP discussions, and then you end up people trying to make money from it without necessarily releasing the data. Would that be a sort of a patenting system behind it to at least have an idea? It really depends on those larger scale decisions.
But a project like this is public money, isn't it? This is countries collectively putting billions of dollars into the Large Hadron Collider. And I think in the case of Large Hadron Collider, that is open data, isn't it? So researchers here at Auckland University are actually working on that data. As soon as it's up on the servers, they can tap into it. So hopefully that sort of thing would continue for all of these sorts of projects.
This one here, the square kilometre array, there's some discussion about IP coming from the algorithms that are developed.
Right.
Not from the raw data, but from the specific algorithms. So that's one of the discussions, how accessible is the data in the first place before you can even think about storing it for the greater public good in the future.
Just give me a nod if anyone has any questions, because we want to open it up to your questions as soon as possible.
There is one.
We do have one straight away down the back. Yeah, go ahead.
And I was wondering, you're talking about two very different projects, the telescope array and the dark matter detector. It strikes me that the dark matter detector is there for a specific reason. It's kind of, your data is, yes, the crystal is glowing, or no, it's not. I was going to say, it strikes me that there's a ton of data with the dark matter detector that you could throw away, because actually you're either answering the question or you're not, as opposed to the telescope where actually you care quite a lot about all the data because you don't know.
You don't know what you're going to find.
No, that's a very good point. I think the Sabre is designed specifically for one task, while the telescopes are really a catch-all, and then the algorithms are designed for one particular task. So you're right.
So
would be my answer to that.
So I guess the question was, is the plan therefore are we not worried about the storage of data from those types of experiments?
From a Sabre one, you just simply want to be there when it happens. That's probably all that matters on that one. But at the same time, it's always, if the Sabre one is literally these crystals that are so pure that you would should be able to detect dark matter, the radiation from that. If I put on my scientific thinking, I'd still want to see what else was going on at any point, just in case there's something else going on that I don't know. But you're right, it's much more limited in terms of what you need to know about that than, say, genomics or the other astronomy, where we're catching everything, trying to read it, trying to work out what's what. The countries, that's probably really the geopolitics of that, and the fact that those countries put in bids. Yeah, there would have been other countries that might have, could have, but didn't. So there was a number of countries that put in bids. Out of those two were chosen. The Southern Hemisphere is a good question. Do you have any immediate answers?
No.
I think it is just like with the Sofia Telescope that we see the Milky Way differently. So it's not just a different side of this.
You've got an answer to that?
I have a partial answer.
Yeah.
Okay, good, go for it.
Those two sites are not the only sites that offered bids. There were sites in China and other places, and the single biggest requirement was the radio silence.
That's
right.
Yeah.
Yeah, good point. Yeah.
I mean, where
else?
on the east coast of North America could you possibly find radio silence?
Yeah, that's exactly.
Yeah.
As an ex-South African, so where is it in South Africa?
There is a site in South Africa
Can I connect
itself.
you with can I connect you with the woman who was on the same trip from South Africa? She'll be able to give you all the. She's really kind of completely knowledgeable in because there's multiple sites, and some are still under negotiation with the indigenous people, and there's sort of land access rights and things. So some are under negotiation, some are already released. But I'll happily connect you with her because she was just impressive in how much she knows about that site.
Botswana as well, So initially it was a competitive thing, and we thought New Zealand and Australia sort of had it, because for that very reason, the lack of radio interference and all that, and New Zealand would have a telescope down here as well, and it'd be all this massive amounts of data going back and forth across the Tasman, and then the IT industry got really excited about it as well, because we need a bigger cable going, and all these things ballooned, and in the end it was like inefficient to do it that way, and ultimately with the GFC, that's when about the time when they were negotiating this, they thought, this is going to be a $15 billion project over time. Let's amalgamate this, and for geopolitical reasons, get the developing world into it as well. So I think it's good that they've done that. But there's going to be a lot for the African continent. I mean, they're hiring engineers left, right, and centre, which is a great thing. Yeah. We'll go to the back there, and
This project is a very interesting one in that it highlights a particular development in science about the big supranational projects, which are huge in data, and effectively what happens afterwards is the data are mined for specific questions, and presumably, or one would hope, that the organisation around the development of those projects talks about data storage and archiving as part of the development of that. However, for most scientists, it's much, much smaller than that, and I'm wondering if I can derail your whole talk by coming back towards data storage in a New Zealand and a New Zealand scientist's context. If you want to do that now or later, but I wouldn't mind having a bit of a crack at that, because I'm a retired biologist who started in the early 1960s and retired a few years ago, and went through a transformation where everything was in paper with the standard public service ethic, thou shalt record everything, sunshine, and it goes onto a file, and much of the material is from all the GSIR or other institutions is lodged in National Archives, and you can actually see it there. And then the transformation with the business concepts of land care and all these other CRIs, the universities have become more business units, and public services, which employ scientists, have their own independent electronic systems which you can't find data from 15 years ago now. It's just utterly impossible. So that most scientists now have this great fear about when they retire, what the hell is going to happen to this wonderful archive of material that they've curated through their working lifetimes. There is absolutely nowhere to put that. And often we retire with huge boxes to our homes because nobody lives there. And we've got them, and we're looking for somewhere to go. So the old question becomes about who would curate that? It's not so much initially the method, it's who. And in New Zealand we have no science archive at all. The Royal Society's never even addressed this on behalf of science. It's one of their naughty things really. But now that we have to have everything put into digital format, wherever you work, is that's lost if your own hard drive or a storage system goes down. So I'd like to have some discussion about who should do that in a New Zealand context.
Shall we bring up Lynn at this point? No, but I agree with you because I think it's a bigger question of this transition to a digital age. That a lot of people will have a lot of stuff, and it's for all of us. I can say the same for Radio New Zealand. There's a lot of stuff produced pre-digital that was stored on CDs. The CDs don't live forever, and then you partly digitize it as best you can, but then what do you do with the digital copies? Where do you put them? Who's going to look after it? Who's going to decide which ones to keep? So I think it's a broader discussion as to how do we decide what to save. But do you want to, in terms of just who could possibly hold a science archive like that, if I give you this mic?
And coming up here, Lynn, so you're in the shot.
I think other people here will have opinions as well, and I think it is a really huge challenge, I think, for institutions like ourselves and for archives, which are the natural repositories of a lot of this output traditionally, and I think it is a really huge challenging transition that we're going through in terms of the people that create that material and getting it, having relationships with institutions like the National Libraries to get their papers there, who have traditionally done that, to move into that kind of relationship with us around their digital output, and it's the same for archives who have a similar program to us. I think one of the big challenges around this kind of material, and it'll be interesting for other people's opinions as well, is some of it is about the size. Some of it is that I think there has been lags in terms of funding, in terms of some of the projects that would traditionally have looked at or been part of the keeping that, setting up standards, setting up processes to keep that material that are lagging behind. I know that MB has started to look at when they give grants for science, that there is now has to be a component about before they'll get the full funding, that they deal with storage, that they look at those kind of archiving and storage issues. And there is an organisation called NESI that is starting to look at some of those big science infrastructures. But I think it's not only in science, but I think in a whole lot of aspects, it's a huge issue for institutions like ours and that distributed, like, as you said, the Royal Society. And Peter had an interesting point about that when we were preparing for this, around all of those bodies starting to see that output, that we have to put a lot more planning and cohesive strategy into working to make sure that they are covered by, a lot of the agreements or processes that have been traditionally for paper material, but other people might have. Certainly, in terms of the National Library, we have the legal deposit legislation, which means that for published material, that whether it's digital or non-digital, it comes here, and the same with our archival collections, which are now, becoming more and more born digital. So, we definitely, institutions like ours, have to meet this challenge in terms of bringing in material that is digital as much as we have done with physical, for us to say fit for purpose, because we are there to reflect all of New Zealand and all of New Zealand's kind of endeavours and outputs.
Yeah, just add there quickly on the Royal Society. So recently they put out a report which was all about taxonomic collections, so dead bugs basically, that scientists will refer back to again and again, and there was a fear that this knowledge was going to be lost because a lot of taxonomists are reaching the end of their career and retiring, and they're not being replaced at the same level by the Crown Research Institute. So they recommended, the Royal Society, that there was better resourcing of taxonomic collections and the maintenance of them, and that did actually equate to some extra money in the recent budget. They allocated more money for infrastructure for that type of thing. But when it comes to digital stuff, it's sort of like it was in the early 1990s, when literally the internet was maintained by well-meaning engineers at universities and in some cases Ministry of Defence or the Department of Defence in the US. It was a bunch of well-meaning people who started that and kept hold of that infrastructure and all the servers that ran the internet in the early days. And it sort of feels in some respects that we're at that level still when it comes to storing and curating data, is that a lot of well-intentioned people have big sets of data, but there is a lack of funding to centralise that and curate it in one place so that it is accessible long term. Most of them will open that data if you ask for it, but there's no one central place or one central organisation that owns it.
Applies to real things as well as digital things.
Yeah.
You think of geological collections sitting in one or two different places, biological collections sitting in different places, sometimes in people's homes still, because that's the only place where people can take it. That's an issue for both real and digital.
I think there's a question here first, and then we'll jump to you. Yeah.
I thought you were just saying that.
No, I have a related. Actually, it's a very usefully related question. So my question was along the lines of scholarly discourse, and do you see that significantly changing as we adopt different publishing mechanisms? We've already talked about repeatability. We've talked about providing the data alongside the paper, and if we assume the premise of publish or die, the emphasis on science is still to publish and to make papers of sorts, or to make defensible pockets of information. What do we do then about referencing and should we be collecting all of the cited papers with the paper to maintain a cohesion along with the data set, along with the software or scripts or algorithms, and what's your sense of what that's going to look like over the next few years?
Just in the increase of information, and it's a really broad sense, the increase of information, I'd imagine that we will, as individual scientists, no longer be able to go right back to source, just because that journey would become longer and longer and longer. What that means, though, for the quality of the new science, I'm not sure. I kind of see both, but that journey back to go back to the raw material will become too big an ask, really.
I think what you're talking about is being attempted and it's being done, but it's usually on a commercial model. So there are companies. There's even one in New Zealand. Publon's was based here in Wellington, is now based in London, and they were looking at putting a lot more of that information in one place. Citations, unofficial reviews. People could go and review a scientific paper, and that would be there as well. Social media data as well. There are lots of companies. And each academic now will subscribe to either Researcher ID or Google Scholar or academia.edu. So there are lots of them, but there's always a business model behind it. So where is the one place that this is open to everyone, freely accessible? Because we are moving into open access. The UK government has said that all of its research that's funded by the public money in the UK will have to be publicly accessible. That includes Nature papers, Science, BMJ, Lancet. I know they're considering that here as well. The Royal Society journals, they publish several journals that are behind a paywall at the moment, but for the first month they're freely accessible. When do we get to the point that it's completely accessible all the time, and what's the financial consequences of that? That's the real issue at the moment. Any other questions? Sorry, actually the chap in front of you I think was waiting next. Did you have one? Yeah.
Yeah, you had
I have lots of them.
That's right.
Just the world hasn't even fully agreed on the issue of openness and accessibility.
Yeah.
One of the largest collectors of data, Google, has had numerous lawsuits prohibiting them from keeping and opening data because, well, it interferes with someone else's commercial interests.
It's a crux of it.
The issue you raised, your comment about who owns, well, that's not actually likely to encourage the proper curation and preservation. It's more likely to enable the destruction for scarcity purposes by vested interests.
Yeah, good point.
So your argument would be that if it's in smaller pockets, then even if some of them go off, it's a smaller risk. Than,
because that's like, you know, in terms of encouraging innovation.
Yep, I'd have to take that point quite heavily because you're right. Yeah, it is a bigger. You know, when coming back to the topic of this week, the preservation of it is that is the crux of it all, really. You know, who is producing the data in the first place? How is it funded? What's the access to it? And how then can we make sure that there's at least some completeness in what we have? But really, we're kind of, it's a non-digital issue as well with having complete collections.
Yeah. Time for a couple last questions, if anyone has any. Just briefly, absolutely, yeah. You know, when I first moved from technology into science, I thought I would be going out into the field a lot more than I am. Oceanographers and that spend most of their time in front of computer screens now, looking at data that someone else gathered. So that's the nature of science now, and people build their whole careers and never actually. I know an oceanographer who went out on a boat for the first time on Tangaroa on a big expedition, you know, for the first time, and had been working on data that other people had gathered and sent, and it turned up as a, you know, on his hard drive. So yeah, absolutely, I think it's changing the face of science completely.
Yeah, same here, and I think the plus of that is that we can now use a drone to get data that people may not even necessarily be able to get, or use a drone to drop off bait in a place.
Yes.
Predator free by 2050, not by 50. By 2050, predator free. So you can use a drone to drop off bait deliberately in a place where you couldn't even access as a tramping person. But yeah, the same that the field trip where you go and gather specimens is becoming rarer, and you meet a lot of people who, like you were saying, have never actually been anywhere. Like Alan is saying, you know, he doesn't need to go to this site because he gets the images that are produced for him, and that's where he spends his time. So his lab is a computer screen, and the supercomputers behind that. More of that.
There's a centre in Auckland. It's called Te Pūnaha Matatini. It's the Centre for Complexity, and pretty much all the people who are working there are data scientists, and they're working on everything from, they've collected cell phone data from around Auckland in conjunction with a mobile phone operator, so they can see the flows of people at certain times of the day around Auckland. They're looking at predator data as well, social welfare data. So in the age of big data about us, there are researchers now, social researchers, data scientists who are looking at all of this data that we are producing on social networks often. I mean, Google and Facebook give access to researchers to sets of their data so that they can gain insights into society, and to some extent they know more about us than we know about ourselves by looking at some of these trends.
There's data journalists now as well.
Yeah.
So beyond science journalists, there's now people in the journalism profession working just on data journalists. I think, it would be nice to see the discussion about, just back to New Zealand, you know, what was raised earlier, back to New Zealand, to somehow think about, do we need a place for the New Zealand things that are openly available? So that way we could at least gather what is in the open space into either one digital space, but also one physical space would be nice, so that as a researcher coming from anywhere at any time, you know where to go, and you know that the type specimens of whatever, whether it's a bug or whether it's a piece of rock or whether it's, you know, whatever type specimen there is, that you will be able to find them, that they're not hiding in somebody's attic, because that's the only way that scientists could keep things, to take them home with them, or they're not hiding in some drawer that the curator who was looking after that collection before is no longer there. And that would be a starting point to think of a New Zealand collection place, digital and real,
Yeah.
virtual and real. Is the National Library a place like that? I'm not sure.
We're sitting in it.
This is it, yeah.
Yeah.
Between archives and the National Library.
Yeah.
I mean, it's the...
For science. I mean, is there scope to have a science space where...
Papa, which is, traditionally had really big science research collections, and they are certainly also starting to look at what that means when the science they are doing themselves and the science outputs that they get.
But they won't archive data from people who don't work.
No, I know, and I think your point, your point is the absolute nub of what I think we are facing at the moment around science data.
I really would like to see a bit of leadership on the particular topic, initially from the Royal Society, because that is where this whole, I mean, they are there to represent the interests of science in New Zealand. Okay, they've been taken over by the government and they're basically a government department, but it would be nice if they showed the independence of mind and used some of the people who are the scientists of New Zealand to actually come together to help them to do that.
Yeah. Well, look, as I say, they did that with Taxonomic Collections, which had some impact. So the next phase is the digital realm as well. They should definitely be having a look at that.
Okay, that's a message for you to take back.
I will. I will, no doubt.
But also that situation that you described, somebody retiring from their job, is it within that institution that they're in that there should be some process of actually taking whatever was produced in that career and making sure that it isn't lost in your attic, or in somebody else's home, but put away somewhere where people can continue to access it.
So thanks so much for your questions.
Thank
and
you
thanks
for
so much
coming.
for coming. Appreciate it.